This series is about getting inside the stuff we just can't live without. The cleaners, the cosmetics, the convenience items that we use every single day. How do these things actually work? I'm Jane Moore, and I'm on the hunt for the hidden science in my daily essentials.
Oh my God.
I'm determined to get to the bottom of what's doing the clever work inside the stuff we buy and rely on, and find the secret wonderstuffs that we take for granted. It will lead me to the brink of utter humiliation, test my senses to the extreme,
I'm actually going to retch.
and push my nerves to breaking point. And if I survive all that,
I'm expecting to go down the supermarket aisle with a newfound confidence in what I'm looking for, having discovered what really does the job.
So far, I've learnt about some of the astonishing stuff that works its magic in keeping our homes spick and span, our clothes washed and scrubbed, and our bodies cleaned and preened. This time, I want to pull apart 3 of our most trusted domestic lifesavers, which I, for one, certainly wouldn't want to live without.
Wow, look at that.
I'm talking about drain unblocker, antifreeze, and batteries. To help me in my quest, I'll be calling on the services of the professionals, including our resident Wonderstuff guru, Dr. Mark Miodownik, head of the Materials Research Group at King's College London. Later, Mark will be trying to blind me with science once again.
Plastic.
By attempting to recreate the world's oldest battery from a jumble of bits from his toolbox.
This isn't going to explode, is it?
But first, to tackling an item on our supermarket shopping list that we all hope we don't have to buy very often, but when we do, it's an absolute lifesaver. My Wonderstuff hunt starts with one of the most infuriating household problems of all, a blocked sink, loo or drain. When a bit of plunger action has no effect, I reach for one of the many chemical unblockers on the market. But what does your typical drain declogger actually do? And is there a particular Wonderstuff that they have in common? To get to the bottom of what causes this nasty problem, I'm heading out on the rounds with professional drain unblocker Terry Kaufman. So what's the most common problem that you get called out for then?
The most common problem I would say is wet wipes. Because a lot of people are using them. On telly they say that they dissolve and they break down. But they don't.
What's one of the funniest things that you've sort of found down somebody's sink where they've said, oh, I don't know what's down there?
With the sinks, it normally is grease and hair.
Yeah.
But drainage-wise, you can find pretty much all sorts. One guy came home drunk one night and he's flushed his underpants down the toilet, and we had to go and fish them out.
Oh, we've all done that, Terry. We've all done that. Oh, blimey. Without working drains, any building quickly grinds to a halt. Right, let's go. Right now, it's Orpington College that has a major blockage. OK.
Right.
I've changed some nappies in my time, but nothing's prepared me for this.
This is the normally the manhole that they have trouble with.
If you're eating, look away now.
Right, as you can see, that's...
Oh, that's... Oh, how do you do this job?
It's the same as everything, you get used to it.
Fortunately, my own block drain's never quite this bad.
So this is like a sort of a grand version of what you'd get in a domestic house, really?
It is.
Yeah.
Yeah, it's the same thing.
This is just the overflow. The logjam must be somewhere downstream.
If you come round here...
Yeah. Ah.
And look at the pipe there, you can see that is the cause of the problem.
Oh, yeah. A big plug of goodness knows what. Oh,
That's it.
It's just like what happens when grease, hair and other yucky stuff builds up in our pipes at home.
Right, OK, Terry, off you go.
OK, then.
It takes a lot of hard work with specialist equipment to shift it.
Hey! We have liftoff.
Thankfully for your typical smaller-scale household blockage, there's somewhere to turn before calling in a big gun like Terry. Yes, I'm talking about the staggering choice of chemical drain cleaners. And judging by the labels, there must be something in here that's strong enough to do the dirty work. So what exactly is it? I've asked the University of Warwick's chemistry department to demonstrate what's in Drain Unblocker that makes it effective. So they've built the ultimate household blockage, a stomach-churning cocktail of melted lard, bits of old veg and hair, kindly donated by chemist Julie Ann Loch.
It's not like cleaning your dishes. You can go in and have a good scrub with it. This is a case where we really have to get chemicals to do all the hard work for us.
Julie Ann is going to make some drain cleaner from scratch. Whatever you do, don't try this at home.
I'm going to get you to put on a pair of gloves.
So what would it do if it went on my hands?
It would eat through your skin because your skin is fat.
OK, I'll put the gloves on then.
So you think that it's going to eat through the fat in this drain. So how easily would it eat through all the fat, the surface of your skin?
Yeah, that figures.
So we're going to make up some caustic soda.
OK.
So I want you to hold on to this, and I'm going to pour in some water.
Julianne's starting with sodium hydroxide, which apparently is the linchpin of many off-the-shelf drain cleaners. When it mixes with water, the result is hot stuff.
Wow. That is seriously hot. What's happening here?
Isn't it? Well, we'll have a look and see how hot it is. So it's flying up the thermometer gauge here. It's just coming up on 60.
Julianne tells me that the particles in the mixture are violently attracted to one another, and that this chemistry is releasing a lot of heat that makes the thermometer shoot up.
It actually feels like boiling water.
Yeah, it gets up to that stage. And this heat will have a really important role to play in how it cleans your grease.
To be on the safe side, our self-styled blocked drain goes into a fume cupboard.
Starting to eat through it now.
Wow, look at that.
Yeah.
You can visibly see it going down.
On our thermal camera, you can really see the sodium hydroxide at work. Already the mixture's as hot as a cup of tea and it's starting to melt the fat, but that's not all.
So what you've got here is you've got two really exciting things going on. The heat of it then is helping with the cleaning. And also the sodium hydroxide is turning your fat into soap.
Ah, yes, I remember that from my travels. Alkali plus fat equals soap. And this will help clean your pipe. Amazing.
And also, the sodium hydroxide is breaking down hairs. Hairs are basically long chains of proteins which are made up of amino acids, and the connection between each amino acid is very sensitive to big, strong alkalis. So that helps break down your hair as well.
But it's still not quite enough to shift our mega blockage.
You kind of feel that you want to get in there and give it a good old oomph.
A good old bit of a stir
which,
there.
of course, we wouldn't be able to do in a real pipe.
What we need is a bit of agitation, and Drain Cleaner has another trick up its sleeve. It can also contain aluminium, which reacts with the sodium hydroxide to give off lots of bubbles.
God, look at that.
Because this is releasing a bit of hydrogen gas here.
Wow.
Yep, you see? Nice bit of hydrogen. So this is reacting with your sodium hydroxide.
That's amazing.
So not only is it doing the bubbling, that's what you're getting. All these bubbles of hydrogen gas are released.
Wow.
That's hydrogen gas there. So all these gas are helping to agitate things in there and move stuff around.
And finally, it's time to say goodbye to our revolting blockage.
Look,
Here we go. We have liftoff.
we
Here
have
comes our big
completely
clog.
perfect.
We have a beautifully clean pipe. There we are. You know, in the past, I've just kind of got the old drain unblocker out from under the sink and poured it down. I haven't given a second thought to how it works. I just kind of know that it does what it does. But having done this, I'm never going to look at it in the same way again. It's absolutely incredible.
To me, this sodium hydroxide, or caustic soda, is a real wonderstuff. We've relied on its cleaning properties for thousands of years. It's indispensable in drain cleaner, but we also need it to make essentials like soap, paper, food, soft drinks, and even CDs. And it's caustic enough to strip paint and decompose dead bodies. When it comes to fixing or thwarting some of life's most infuriating binds, then we just had to throw the spotlight on this stuff.
Antifreeze. Time and again, it rescues our cars from the worst excesses of the British winter. But how does it do it?
A good starting point for any chemist to solve a natural problem like freezing is to look at how nature tackles it. There are plenty of animals that manage to keep moving in sub-zero temperatures, and Professor Lloyd Peck at the British Antarctic Survey has a veritable cold water menagerie, which includes these little bundles of delight.
Oh my God.
They're one of the big groups of crustaceans, and that's isopods. And wood lice are isopods.
Take it. Oh God, I can't bear it. It looks like a big...
The sea louse can survive to just under freezing point. But if I'm to find the science that keeps things moving at much lower temperatures, this isn't it. Down the corridor, Dr. Roger Warland reckons he's got something that can survive at record-breaking low temperatures.
These are tiny, what are they?
They're springtails. They're a type of primitive insect that live in the Antarctic. These little insects have to live there for summer and winter.
To put this to the test, some Antarctic springtails will be put into a super deep freeze kept at a constant minus 25 degrees. I get cold just opening my fridge door, so it's back in the suit for me.
Look at that. Kitted up to walk around the supermarket freezer department.
The springtails, however, have their body chemistry to help them.
Oh, blimey, the cold hits you straight away.
OK. Well,
At this temperature, most creatures would die in minutes.
So we've got all this gear on, obviously, to help us retain heat. But if we weren't wearing this, how long would we survive?
without the clothing, at minus 25, you're not going to last very long at all, a few minutes.
A few minutes?
Yeah.
Gosh.
The tiny insects soon stop moving. Despite their nicknames, snow fleas, I have my doubts about this.
I'm really beginning to see the effects of being in here now.
Yeah. It's getting quite chilly.
Yeah.
Isn't it? Yeah.
What's my beard like? Is that all right? Well, these little chaps have definitely stopped moving now.
But back outside, Roger slowly warms up the springtails, and we check for signs of life.
Well, look, this one's starting to move now. He's sort of twitching his antenna.
Yeah.
And his legs are starting to move very, very slowly.
Yeah.
Yeah, so on this one here, look, is that ice I'm seeing? Those sort of droplets on it?
I think it is, yeah. It's just beginning to melt now. They stay in this dormant stage until conditions improve and they can start to become active and feed again.
Their natural antifreeze kept them alive, even at minus 25.
Well, what's happening in all that chemically?
Yeah. They've been converting their food reserves, glycogen, into cryoprotective compounds such as glycerol and various other sugars and sugar alcohols, which all act as cryoprotectants or antifreezes. They prevent the water from actually being able to crystallise and form ice.
It's amazing that something that small can produce all of that.
It is, yeah.
But is this glycerol in springtails the same stuff we use to stop things freezing up? Just up the road at Cambridge University, I'm hoping Dr. Peter Wathers can enlighten me. And he's promised to get his fancy gizmos out.
Look.
Oh, wow, look at that.
The Iceman cometh.
OK, well, let's have a look, shall we? Let's pour a bit out. So this is the de-icer.
It turns out our de-icers and antifreezes commonly contain something called glycols, which are a chemical relative of the natural glycerol made by the springtails.
The key ingredient is something called ethylene glycol, and this is what we've got in here, a little bit of ethylene glycol. So it's sort of slightly thicker than water, slightly gloopy.
But before we can see glycols in action, Peter wants to show me why putting antifreeze in your car radiator is so essential.
Actually using this cast iron flask. This is pretty solid.
That's incredibly... Look at the thickness of that.
Well, actually, I've got one here that we've cut in two here, and you can see it's pretty thick.
But ice isn't going to damage that, surely.
Well, let's see.
The flask is filled with pure water, sealed, then dropped into a chemical bath at a staggeringly cold -80 degrees centigrade.
Oh, my God!
So this is just cooling down now.
Right.
OK.
What's it from Young Frankenstein?
Just back a little bit.
God, it really does look like a bomb, doesn't it?
It doesn't take long before the water in the flask starts to freeze.
Well, that worked.
Well, let's see what's left.
Oh, my God. I think I've just had a heart attack. God, that was a spectacular explosion. Look at that.
Yeah, that was quite a frisky one.
That is absolutely astonishing that ice has got the power. I mean, I'm absolutely blown away by that, literally. Oh, I'm shaking. So that could be a car
Safety glass
engine.
there. Well, the pipes there can easily burst.
Wow, science is really exciting.
OK, so we definitely need something to combat the wanton destruction ice can cause. But can the man-made glycols beat Springtail's natural antifreeze? Just how cold can ethylene glycol get?
So let's give it a go.
Yep.
I'm going to ask you if you can record the temperature, please.
Oh, right.
OK. So you've got the reading there, and I'm just going to cool this in the bath. OK, and the temperature should be dropping.
Good grief, it's dropping like a stone. 2, 1, 0. OK, we're below 0 now.
OK, it's getting gloopier. It's certainly more viscous. So how are we doing for the temperature?
11, 12.
-12.
13.
OK, and we're getting crystals
Getting
here
crystals,
forming. OK, so about -13-ish. We're definitely getting the liquid here. It's freezing. OK, and eventually, if we're kept at this temperature, this would all freeze.
So pure glycols are good down to -13. Not as impressive as Springtail antifreeze, mind you, with their -25. But Peter promises me that glycols have an amazing trick up their sleeve. When mixed with water, the glycol molecules work to make the whole mixture resist freezing much more effectively.
So let's cool it down.
13, 14.
OK, so we're already at temperatures lower than the pure ethylene glycol, -20 now.
Yeah.
And it's still definitely liquid. No sign of any crystals in here. -30.
Yeah.
Still no signs of any crystals.
That's past the Springtails, but how much lower will it go?
It's certainly getting thicker.
Yeah.
But no crystals yet. We're at
God, 35 now.
-35. OK, so this is really quite bizarre. But the pure water
Yeah.
freezes at 0. The
Yeah.
pure ethylene glycol at -12. And the mixture we're at nearly -40. So it's still liquid there at -40, -43. Ah, there we are.
It's starting to now, but just about, yeah. Clever stuff.
So a mixture of glycols and water gives us an antifreeze that can beat anything nature can come up with. What's brilliant is that glycols are doubly helpful in your car because they also increase the boiling point of water, so they'll stop your radiator overheating in summer too. And these Wonderstuffs turn up all over the place, from shoe polish to dyes and preservatives. So far, I've tackled 2 of the major irritations that threaten to wreak domestic havoc on us. But what about something that has to be the ultimate lifesaver, enabling me to live my busy life to the max? It's hard to think of something that we haven't invented a battery-powered gadget for. I know that batteries come in a dazzling array of shapes and sizes, but I've never stopped to think about how they actually work. So, armed with a battery of questions, I'm off to meet my materials scientist, Mark Miodownik, who always has the energy for some answers.
Let's get some drinks.
Lovely.
Well, a battery is essentially a kind of container of electricity. The difference between a battery and the electricity you get from home is that difference between a bottle of water and turning on the tap at home. They're essentially the same thing. So the clever thing is, how do you bottle electricity up into this tiny little container?
So what is electricity?
So electricity is a flow of electrons. So electrons are going from one terminal around this piece of wire up here through this tiny little filament, and this filament is resisting those flow, just the way flow of a river, when you narrow its course, kind of goes faster, and it's so resistant that it gets red hot and glows, and that's a bulb. That's how they work. So the electrons come from a chemical reaction inside the battery. So every time you turn on one of your gadgets and you're using a battery, you're turning on a chemical reaction. If you can get it to happen in a certain way, you're in business.
So if a battery is a carefully controlled chemical reaction, what kind of ingredients are in there that are reacting with each other?
You can make a battery out of any sort of chemical reaction, and with a vast range of materials. Let me show you. I've got some odd bits and bobs here which I can make into a chemical reaction. And, well, I didn't, yeah. Hold those for a minute.
Plastic.
No.
Danger!
Gee, thanks, Mark. And to prove you can make a battery from the simplest of materials, Mark's about to reconstruct something called the Baghdad battery. All you need is a jar, some acid, vinegar will do, and a piece of copper.
I don't want it to touch the other bit of the battery, which is going to be
Is it going to explode, is it? Shall I stand well back?
It usually doesn't, but sometimes...
That's reassuring. And the last thing you need is some iron or steel, like Mark's rather butch drill bit. Jars similar to this one have been dug up in Iraq that are 2,000 years old, suggesting our ancestors could have been dabbling with the magic of electricity long before they knew what it was.
So if I connect one side of the battery, which is the copper, to the other side of the battery, which is the steel...
Yeah.
Yes!
Ah,
0.3 of a volt.
So a normal battery is what, 1.5, 1.5 volts?
An AA battery is 1.5 volts,
Right.
yeah. So this
it's
is...
a bit piddly, isn't it?
Well...
Danger!
OK, so it's hardly surprising that a pickle jar, some copper and a drill bit generate a comparatively tame chemical reaction. But all the same, we just made electricity.
So, I mean, what I sort of thought was incredibly complex, what's going on in here, when I see it like that, it's very simple.
So I'm beginning to understand that creating electricity is all about the combination of different metals. And from the wide range of batteries I see in the shops, some metals seem to be more useful in batteries than others. For a disposable battery, a popular choice is a zinc core surrounded by manganese. It's a reaction that can create a lot of power relatively cheaply, but there is a limitation. There's only a finite amount of power in these batteries before they run out.
The problem with these types of batteries is that they sort of, in a sense, gunge themselves up in the end. That battery will last as long as there's zinc that hasn't reacted.
OK, so although disposable batteries are handy for things like remote controls, torches and alarm clocks, they definitely wouldn't be convenient for the one electronic gadget that goes with me everywhere, my mobile phone.
What we want in those kind of gadgets is them to be rechargeable. So we want the chemical reaction to go one way to give us electricity and then to be reversed if you charge it up in the mains. You want the chemical reaction to unreact. Getting that to happen is the next revolution in batteries, which happened not so long ago, actually. So the state-of-the-art technology, and where all the excitement is in batteries, is a metal called lithium.
Well, if Mark's excited about lithium, it must be worth a look. So it's back to the chemistry department of Cambridge University. At the very least, I'd better get an honorary degree out of this. I'm going to meet Professor Claire Gray, whose lab is at the cutting edge of lithium battery research. So what makes lithium best for my mobile phone battery?
Well, basically it's because the lithium ions are small and they're very light, and that means they can move very, very fast, and they're very, very reactive.
And that's obviously a must-have, because technology, we want it to get smaller and smaller
Well,
and smaller.
absolutely, particularly in smartphones and applications like that.
So the amount of power that these little devices consume demands something very reactive in their batteries. Something like lithium, in fact. To prove just how desperate lithium is to react with other things, anything at all, Professor Gray is about to drop some into common or garden tap water.
You might want to step back. So you
Oh,
can,
yes, wow.
so you can move it around, see it moving around, and it's giving off hydrogen as it's reacting with the
Good
water.
grief. That's incredible.
And so it sort of just shows you just how powerful this is.
Yeah.
I'll
It's
rescue
actually
it quickly.
fragmenting.
Yes.
I mean, the one thing I notice is that it's metal and it's floating.
Yep, and that's because it's such a light element. So you can see up here, here's lithium, and so you start off with the lightest element, hydrogen. helium, and lithium is the third one, and it's even lighter than oxygen.
A metal that's lighter than oxygen and even reacts with water. How on earth do we turn something like that into a battery?
So this is actually the inside of one of
exactly.
the... Oh, wow.
Exactly. And so you can see it's made up of this roll, and the roll contains different layers of different components.
These 3 paper-thin layers work in much the same way as the metals and liquids in ordinary disposable batteries. The key difference here is that the metal itself moves between the layers as it reacts. And the really neat trick is that recharging the battery pushes the lithium back where it started.
So when I charge, the lithiums will come out of this material, they'll go through this separator material, and they'll be trapped inside the carbon. And when I discharge, they'll go back in the opposite direction.
So as the lithium particles flow backwards and forwards between the layers in the battery, their electrons are channeled backwards and forwards too, but through our laptops and phones. Professor Gray has a microscopic video to prove it.
So these colours that I'm seeing here, is that literally the lithium moving across the battery?
Yes, you're watching the lithiums being inserted into the carbons, and because lithium is so small, it actually doesn't distort the materials.
You can't kill the metal.
So lithium's minute size means it's not only light, but it can flow quickly through a battery without damaging anything. Meaning lithium batteries can be recharged again and again, regardless of how full or empty they are.
OK, so I've really got the benefits of lithium now. It's small, it's light, it's reactive, which gives it a great sort of power punch, and also you can constantly recharge it.
Yes, so lithium-ion batteries are really a technology enabler. Without them, you wouldn't have your mobile phones, you wouldn't have your laptops, and it's really revolutionised the whole area of portable electronics. So it really is the sort of wonder material.
So it's official. Even a professor is calling lithium a wonderstuff. As well as revolutionising our portable electronics, lithium is finding all sorts of other futuristic applications and is also the gold standard in mood-stabilising medication. It seems that lithium is a tiny molecule that punches well above its weight. When I set out to discover the wonder stuff behind the things we use on a daily basis, I truly have no idea what I might find.
The bottles and packets were familiar to me, but I really knew very little about what was actually going on inside, working its magic.
I love the simplicity behind some of these discoveries, that the simplest solutions can often be the most powerful. That just adding something as basic as water to sodium hydroxide can create enough force to clear the worst of domestic crises. And that the clue to solving the problem of a frozen car engine lies in a tiny primitive insect that lives in the Antarctic. Simply amazing. Next time, I up the ante on my hunt for life-saving wonder stuff as I uncover what protects us from the killer germs around our homes.
So that's pretty badly contaminated.
That's off the scale.
And in our toilets. And Mark's technique goes from bad to worse as he attempts to explain smells using his trainer.
I don't have to smell it. I can sit. Oh, look at that. It's all damp and scuzzy.